Rajesh. Going forward, it is my pleasure to introduce Dr. Shipi today, who will be our speaker for this entire first week of the summer school. Dr. P is a member of faculty at the Institute of Theoretical Physics of the Chinese Academy of Sciences and a visiting scientist at the Kavli Institute for Physics and Mathematics in Tokyo. He completed his PhD from Peking University in 2013, after which he went on as a postdoc to the Asian Pacific Center for Theoretical Physics and the Chinese Academy before joining the faculty at the Yukawa Institute in 2017. And from there, he eventually moved to his current position at the Chinese Academy of Sciences in 2020, which is just last year. He's a long-standing expert on early universe cosmology, cosmological perturbation theory, and the stochastic gravitational wave background, of course. And this week, he will be telling us all about the fundamentals of the stochastic gravitational wave background from the early universe and how we can bring it within our reach. So before I ask Dr. P to take it away, may I quickly request the listeners to bring up their questions that they may have during the lectures over chat or perhaps at the end of the lecture. So Dr. P, do you want to take it away?
Hello, everyone. Thank you very much for the introduction. Can you hear me?
Yes.
Yes, sir.
Yeah, okay. Thank you very much for the invitation. So shall I share the screen to the can you see that? Okay, great. I'll just start like this. Is it okay? Yeah,
Yes.
if you have any questions, yeah, just as I said, just type in and read it to me later. So, today and this week, I will introduce some basic ideas about the stochastic gravitational wave background from the early universe. So I will start with some overview, which I will briefly introduce what I'm talking about in this week, but with some kind of very rough estimate of the numbers. We know that the gravitational wave is something that can perturb the metric. So roughly speaking, it is something like this. I just focus on the so-called H-class polarization, if you remember correctly. But this is, I think, this is something that we can start with. And this H, which we sometimes call the characteristic amplitude, has a equation of motion, which is a waveform. So its solution is exponential. Let's see, so it's minus I omega t plus a k times x, something like this. So this is what we can learn from its wave nature. So this characteristic string is proportional to the change of the length divided by the length itself. As we know that we detected this gravitational wave by the interferometer. So we have a laser gun here and go to split into two in x-axis and y-axis and go back and forth to some mirrors. And the difference between this x and two axes of delta x, Lx, delta Ly can be measured to a very high accuracy by the interference. So that's the reason why we can see this relation, that the amplitude of the gravitational wave can be well measured by the interferometer in this way. So, okay. I think you can see what I have seen here. I drew a small interferometer like LIGO-like stuff. So we see the gravitational waves from the binary stars in this way. So laser goes, let me change the color. So laser goes here, And with the splitter, and it was split into two perpendicular beams in here and reflect by the mirror. The key point is that the difference in the length it measured by the laser is delta xy and delta x, both of which can be characterized by this character of h. So h is proportional to delta L over L. So this is the exact quantity we would like to measure in the experiment, and it's connected to the change of proper distance in the metric. So this is the first thing I want to emphasize. And also it is equivalent to see as the distance of the Earth and the millisecond pulsar. That's the other method. We can measure the amplitude of gravitational waves through the pulsar timing array. And for a stochastic gravitational wave background, this gravitational wave comes from every direction in some different amplitudes from different angles. So in this case, it's very difficult to localize, but we see some noise-like stuff, which is a specific spectral density or spectral structure of the spectral density of the energy density parameter. So the key point is that how to estimate the energy it has taken via this gravitational wave from the background. I will talk about the source of the gravitational wave background later, but now let's first define the energy of the gravitational wave. And this is the main content of the lecture I will have today. But I have a very simple idea to estimate it. So for instance, we have the proper distance. Let's say dl. This is changed as 1 plus h. Let me just get 1 plus h dx squared. So it's something like this. Or dl is 1 plus 2 or h of dx. However, we can make an analog of this. Sorry, I have logged out my. Let me think. Okay. Sorry. Okay. Yeah. So the proper distance is the difference of the coordinates, co-moving coordinates, and some kind of something that is in analog to the scale factor. This is just an analog, okay? So maybe some of you remember the Friedmann equation in cosmology, which means that the energy density that can change the shape of space-time, can curve the space-time, is proportional to the Planck mass squared times the Hubble squared, where the Hubble is a dot over a. A is the scale factor, which is just here. So this is 3mp squared over h dot divided by 1, right? Because this h is small, so a is just 1, but its time derivative is h dot. So this is mp squared h dot squared, as I said. And we know that it has a nature of a wave. This is what I have written in here. So you can immediately see that a time derivative of a wave is equivalent to this special derivative, which is proportional to k. So this is in turn k squared h squared mp squared. And the correct answer is k squared hc squared divided by 16 pi g a squared, if I remember correctly. Okay, yeah, this is the correct answer we will have later. Let's see. So this is the trick I have to derive the energy density of the gravitational wave. I will come back to this in more details later. And then the next task is to study how much is the characteristic amplitude of the gravitational wave. So to do that, let's emphasize that this is lecture 1 we will have today. I hope I can finish all the content I completed here. And in the lecture tomorrow, I think I will talk about the cosmological perturbation theory. In FLRW universe and in inflation. And because to make an accurate calculation of all these quantities, a complete study of the cosmological perturbation theory is needed. So that will be the lecture tomorrow. And for Wednesday, I think we will talk about the primordial gravitational wave. That is also very interesting, but I can just estimate again as the amplitude here. So for instance, because we know that this is the energy density, that's it. Then we can guess that the action of the gravitational wave is something like this. Right? And in this case, because during inflation, the universe has a finite horizon, which is order 1 over Hubble. So this is dt h inflation to the cube minus cube and p squared h dot squared. I borrowed this idea from Slava Muganov's book, but he's talking about the scalar proportion. The basic idea is the same. And this kind of a special coordinate can be integrated out. The key point is that this system looks quite like a quantum mechanics, as you can see, that you have a kind of a generalized coordinate dot square, something like this. So you have Q, the generalized coordinate is on this one, right? And then you take the generalized momentum, it's similar, just a dot. And then you take the dot out, as you said, during inflation, a dot means times the time factor, which is just Hubble. So it's Hubble minus 1/2 MP times h. So this is what we need. And then we use the basic idea of the canonical quantization, which means that the generalized coordinate times generalized momentum is at most order 1. Actually, this is a Planck constant, but I take natural units. So in this case, this is h, now MP over h squared, small h squared equals to 1, and give you that the quantum fluctuation of the tensor perturbation is this number. So in most of the models, the inflationary Hubble constant is like something like 10 to the 15th GeV or something, for instance. But I only have an upper limit for that. The only thing we have is that the similar thing, the power spectrum of the scalar perturbation, let's see, zeta, this is 10 to minus 5. This is something we already observed on the CMB. But for visions, we only to scalar is part of the corresponding of zeta. Basically speaking, is h over zeta squared is 10 to minus 9 or something. So this gives us h is 1/2 of zeta, that's smaller than. This is like 10 to minus 1, let's see. So times 10 to minus 5, so it's 10 to minus 6 at most. And then we will talk about the propagation of such waves. So this is something that is, I think is very trivial, but for non-cosmologists, science becomes a little bit complicated. Anyway, the big picture is that the gravitational wave in the radiation-dominated universe stays, evolves as the same as the background. Maybe you cannot remember the time evolution of the universe. Let's say, so we have inflation. Let's just remind you, we have inflation. And then usually the radiation dominated universe, where the A is proportional time to the 1/2, and matter dominance A is T to the 2 or 3. So the equality happens at like 10 to the minus 3, something like that. So this is like A is, if we use A, it's like 10 to the minus 18 or something. So the key point is during the radiation dominated universe, because the gravitational wave is also radiation, so it will evolve as the background. So this means that the portion that cosmologists usually use as omega GW is defined as the energy density of gravitational wave divided by the background energy density. Let's see, we'll see. This is the critical density. So this kind of thing stays a constant during radiation-dominated universe. So this is because, let me just draw a space-time diagram for that. So we have a, I think this is one. So this is A, and this is the physical length. So Hubble horizon is proportional to A. And I think this is A squared, is 302 in the method. Something like that. So you have different modes. We enter the horizon. This is the gravitational wave with K or A, with the wave number. So we enter the horizon for two of the modes, we enter the horizon both in the radiation dominated universe, but they stays the same. The omega GW stays the same for both of two. But there is a unique, a universal redshift factor from here to here. This is what we have now, is 0. So this is a equality, which is 1 over something like this. So there is a factor of this large that can make the gravitational wave parameter decay. So this one stays the same from after inflation. Let's see, in reheating. Let's reheating. So after reheating, to if you can define this. I will talk about this later. Okay, it goes to equality. This is a constant, but it will decay as 1 over A because of this redshift. So which give us that omega GW is 1 over A times the primordial value. Let's see. At the horizon crossing. For instance, during inflation, we have this manner. Let's say we have 10 to the minus This is just proportional to the power promoted power spectrum. This is like 10 to minus 11, 12, or let's say 12. And this factor, they said, is A not divided by A, the other way around. So T divided by A not. This redshift is 1 plus the EQ. Sorry. Yeah. This is so keep them together. You have this is 10 to minus 16. This is the primordial gravitational wave amplitude we can observe today. Let me draw the picture. So this is the frequency. This is omega GW. It's like 10 to the minus 16. It goes something like this. There's other things. First of all, you have a frequency 2 minus 2 tail in the low frequency side at around 10 to the minus 16 hertz. This is roughly speaking is the frequency which re-enter the horizon at matter radiation equality. Because if it re-enters the horizon in the matter-dominated universe, then there is a difference. Like if you see it here, it evolves differently depending on the time it re-enters the matter-dominated universe. So we can derive that result frequency to my, and if the influence stays oscillating in an equational state which is equivalent to that of matter, which means that, for instance, the power, the potential of the inflation is something like this, then the average or equivalent equational state Okay, I talked about something in here. So it says that my internet is not stable. Anyway, so if I have any problem, just let me know. It's the same thing that we have in the standard reheating in the quadratic potential, that the amplitude of the gravitational wave parameter decays as frequency to -2 as is expected. So it's the same in here, and here, and it's a plateau in here. But the key point is that this plateau is too low, that is beyond the scope of any of the detectors in the near future. So we have to find a way that in any case that the gravitational wave from the early universe can be detected. So that goes to the next part of this lecture. Anyway, so this is lecture 4. And in the last lecture, I will talk about some method to make the gravitational wave from the early universe large. For instance, if we have a blue tilted, blue primordial power spectrum, then this just will go up. And also, we have non-standard cosmology. Roughly speaking, is W larger than matter. This will also enhance the make the background decay faster, and in the same manner, the omega GW just go up. And also, we can have induced gravitational waves from a scalar perturbation.
This is because, in some sense, to have blue-tilted tensor perturbation is very difficult, but to have blue-tilted scalar perturbation is much easier. And also, there are some other phenomena that is connected to this scenario, like the primordial black hole formation and stuff. This is, in some sense, a very hot topic recently. So this will be the lecture 5. I think I have roughly introduced what I will talk about in the next 2 weeks. So, do you have any questions? If no, I will just go to the lecture 1. This is just introduction to gravitational waves.
Okay, so if you don't have any further questions, I will start to talk about the introduction of gravitational waves. First of all, we have to expand the metric around the flat space. This is our first step. So expansion around flat metric. G mu is G mu r plus H mu. So this is what we have. The key point we want to know is to get out the propagating degree of freedom from this propagation of the metric. So in this case, because the gravitational wave is invariant under the coordinate transformation, we consider a coordinate transformation, or which is called a gauge transformation. So x alpha goes to x alpha tilde, so x alpha plus some infinitesimal displacement of time. So x here is infinitesimal coordinate transformation, and then we have the change of the metric tensor like this: g alpha beta tilde. It's so this is approximately so make this part to be 0 to preserve the variance. Then we have this delta g alpha beta is so when expanding the flat metric, so this one is 0 because we have a Minkowski. Then by taking this is h alpha beta tilde, this is h alpha beta. Then we have h alpha beta is transformed to h alpha beta tilde or x tilde of h alpha beta minus c alpha beta minus c beta. This is what we have for the gauge transformation of the field of the metric perturbation. So now we can calculate the to the Nelian order the Riemann tensor, Ricci tensor, and Ricci scalar. So by noting that The Christopher symbol is some kind of G partial G. So this is just a partial of H. And then this tensor, Riemann tensor or Ridge tensor is gamma, partial gamma plus gamma squared. So it is partial squared H plus some other higher order terms. This is what we might have. So in this case, it is very easy to prove that the Riemann tensor is something like this. I will leave it for the problem 1 for you to solve. And it is very useful in the study of the gravitational waves to define another quantity which can make the gravitational wave equation of motion much easier, which is h bar. So this h bar is defined as h mu minus 1/2 of eta mu of h, or g mu of h, whatever. This is the background metric. So sometimes it's called the metric perturbation. Because in this manner, the trace, if you just calculate, for instance, eta mu nu, so h mu nu is the eta mu nu, h mu nu, minus 1/2 of eta mu nu, eta mu nu h. So this is 4. Then we have this is this is h. So it's h minus 2h is minus h. So the trace is inverse. So in the terms of the h mu nu bar, the equation of motion is very easy. That it is in this way. So the box, the Lambert operator, plus eta mu nu h bar for sigma rho. And this is the equation of motion for this metric perturbation. So to step further, we have to choose the gauges. Let's first discuss how many degree of freedom we have. So this g mu nu is a 4 times 4 metric. Is equivalent to the upper triangle. So actually, the physical degree of freedom of gravitational wave, as we know from the particle physics, is just 2. So we need around 8 gauge conditions to reduce that. The first one we use is the so-called Lorentz gauge. And this is in analog to the Lorentz gauge in electromagnetism. So if you are interested, just read some materials on the history of this name. This is written in this way. So, sorry. So if we have this and look back these equations, you find that this is 0 because it's rho. Let's see. So you have rho, and rho, and so everything is fine. The only thing you have is very simplified equation of box h mu nu is the source term. And it can be easily solved by a green function method. And the sourceless equation of motion is much easier. I will just talk about the sourceless case. So in this case, the gauge condition can be fixed further. I mean, you still have some degree of freedoms after you choosing the Lorentz gauge. This is because that this equation is invariant under a further gauge transformation of x goes to x alpha plus c alpha only if box of c mu is 0. It's very easy to verify that. And then we can construct a symmetric two tensor. C mu nu is C mu nu plus C nu mu minus eta mu nu of C rho rho, which further satisfies the box of C mu nu is 0. Because if you put this condition, then every term in here is 0, then you have this box of C mu is. So given any of this h mu nu here, you have this. You can always add or minus a part of C mu nu to make the same equation hold. And then you can define this as a new mu. So you have degree of freedom of choosing all of these coordinates. So then you have 4 new degree of freedom of choosing this C. So the first one is to use to make the trace h is 0. This is what you can always do. So in this case, because this h bar is the trace inverse version of h, so now we have h mu is just h mu bar after we choosing this. Right? And there are 3 other conditions. Let's see this 2 because we have Lorentz condition. And the other 3 conditions to make the time space part of h naught I is 0. So this is the other 3 conditions. So now you have 10 minus 4 of this Lorentz minus 1. This is h equals to 0 minus 3. This is h y is 0. So you have the 2 degree of freedom left here. And in summary, this is called traceless gauge of h not trace is 0 on condition, and the special version of Lorentz gauge 3 conditions. So you have 4 plus 4 8 conditions, and to fix the only 2. And the hij that satisfy this relation is called in the TD gauge. So it's usually used as a superscript TT. It's something like this. So equation of motion is just this. And after doing so, the only degree of freedom in the Riemann tensor has only one independent component. which can be written as this. I set this to be problem 2, that you can solve that easily. Okay, so it is shown that I will show that later, maybe in lecture 3 or something. So you have many different types of the perturbations in the metric. You have the scalar type, you have the vector type, and you have the tensor type. It will be shown that the only tensor type, the only degree of freedom that has the equation of motion in a radiation type, which means this one, is the TT part of HIJ. So this is the only radiative part that can be propagating outside the source time. So all the other terms are just the Poisson equations, which can only exist when there is a source. So if there is no source, for instance, if there is pure vacuum, then you cannot have the scalar provision, for instance. It can only appear in a fluid where you have the source. That's the key point. So in vacuum, you only have these two degrees of freedom to propagate. And the equation of motion in this manner can be easily solved by and its solution is in this way. So because of the Lambert operator, the solution of this can be written in this way. So it is some function of this. So suppose the gravitational wave is propagating along the z-axis, then it will be a combination of ct minus t for the retarded solution. And this is the we have the Lorentz condition. So partial z of h, sorry, of zi tt equals to 0. So this implies that hzi of t is a constant. It doesn't change with time and space, and so to be 0, because we suppose that at infinity there will be no gravitational wave. Right? The only non-zero components in this manner is the component on the x and the y axis. So we have hxy, hyx, hxx, and hyy. So we have only these two components, and only two of them are independent to each other. Right? So because of the Lorentz condition, hxx is minus hyy. We can write it as h plus, which is a function of the set of this retarded distance, and hxy is h defined as h cross of c minus. Some of these, if you are far from the source, then the functional form of both of these two goes to this manner. So h plus minus exponential I k mu x mu. And k mu is frequency and the wave number. So you can write the HAB this plus cross cross minus h plus times a cosine function of omega t minus z over c. This will be used sometime later. And I just write it here. And A and B is 1 and 2. It is also very convenient to write this formula in a more compact form by a unit polarization to tensor, which is H plus of EAB of plus H cross of EAB of cross. And when I see AB, it's just 1, 2. But I can also see IJ, which is 1, 2, 3, but it's basically the same thing. So because of the traceless and the transverse condition, you have this kind of conditions for them. And the compact form, the concrete form, so EIJ plus is 1 minus 1, 0. And the EIJ cross is 0, 1, 1, 0, 0. In the literatures, some of the authors will put a normalization factor of 1 over square root of 2. So if you read the papers, just be careful, okay? They do it because they want to make the normalization of this symbol simpler. In our notation, we have something like this. E E lambda 2 lambda, sorry. So you can see that plus plus is 1, plus cross is 0, blah, blah, blah. You have this whole relation. And you have some further relation. The most important one is this. Summing over the polarization of two different indices. Oh, sorry. You have this. Remember this K direction okay, I just talk about this normalization relation, and also we have another relation of projections. So we have the same of the polarization, plus or cross, and add them together, then we have a 2 times the 4 tensor of the projector for tensor. So in Magellan's book, he called it lambda projector, whatever. So this can be defined in this way. So first define a 2 tensor of the projector, which is something like this. I use, okay, and let me just use n forever. And So this upper and down doesn't make any sense because they are lower and raised by the special metric. So you can just freely write them in this way. Some people use, for instance, lambda LM, comma ij, but I use comma for derivative. So I just write it in this way. And there are some relations for that, the properties. This is easy to understand because it is a projector operator. It's perpendicular to the z direction, right? And also it is traceless. And finally, you project twice is equivalent to project once. So, yeah. And if you expand this definition in here and here, you get the explicit result for lambda IJKL, which I leave as another problem. And also, you can prove that for an arbitrary metric perturbation of Hij, you can always get, let's say HLM, you can always get its TT part using this operator. This is also the problem left. Okay, so let's go to the third section, frequency analysis. So all of the quantities I have defined in the real space, but I want to in cosmology and also for the astronomers, they usually use the Fourier transformation and do it in the frequency space. First of all, you can expand if you know that the solution of the Hij is a plane wave, then you can expand it in this way. So Hij is Aij exponentially ikx plus Aij star exponential minus Aakx. So this kx means k mu x mu, or the other way around. No. This is because, as I may say a little bit more, so you have the exponential ikx at the special part, and the time variance, let's say of t, this kind of thing is exponential I omega t minus. So we can always have as the plane wave. But in cosmology, things are different. So we cannot do this expansion in 4 dimensions, but we can only do it in 3 dimensions. And the time function, which usually in cosmology we call the mode function, must be solved by the equation of motion. And there will be some extra dependence on time by the scale factor, which depicts the evolution of the universe. I will come back to this later, but now let's assume that we are on Earth and we are observing some gravitational wave from the binary black holes, and everything is plane wave. We do not expect the expansion of the universe. And then what will happen? Okay, so in this case, because the k mu is omega over c over k, and the kt, sorry, kx is omega t minus n times x, then this n is sorry, just the t over t. So d cubed k is k squared dk of d squared of n direction. So in my notation, the n direction is the same as the k direction. And I will just keep using n. Then this htt, sorry, httij(x) is 1 over c cubed of 0 to infinity df of f squared, d squared n, of aij of f n, expansion minus 2 pi. This is the complex conjugate, right? So in the manner I have defined for the eij plus minus, plus cross, I defined earlier, I can expand this thing into a pure amplitude and a polarization unit vector tensor. So this is the sum of lambda, a lambda, and eij of lambda. Sorry. Which is n. So f dependency is here, right? So in this case, the astronomers usually they integrate out the not integrate out, sorry, define the frequency in the amplitude of A. So in this case, this is defined as H tiered lambda. So we have now this sum comes from here, remember. Df d squared n. This is the solid angle. So H tiered lambda f s, maybe s, I forgot. Eij lambda o n exponential minus 2 pi I f t plus c c. Oh, okay, there is s because this comes from this factor. So this special oscillation is also observed in the definition of H tiered. So this is the equation we will use later in the problem. And then for the gravitational waves from a single source, they come from a specific direction. So in this case, it is very easy to write that this aij of k is proportional to some function of f, let's see, aij of f times delta n minus n naught. N naught is the direction to the binary. And we can further kind of simplify this equation. I think what we'll tell more about this next week, but I will just stop here. And by giving you this formula, I think which is the most important in cosmology. As I said, for our cosmologists, usually we cannot do the expansion in 4 dimensions. And by 4 dimension, I mean to have this vector. And this is because you cannot expect the gravitational wave in the universe to be a plane wave, because it also evolves as the time evolves in the case of the scale factor, right? So I will talk about a little bit on the cosmology later, but currently, the only thing you would like to know is that in cosmology, let me just, we do it in this way. So Hij/Tt, or Tx, or eta x, this is the conformal time, whatever, is something like this. We only expand in the 3 dimensions. Okay, and this H lambda is solved by the equation of motion. The equation of motion is something like this. I will come back to this equation of motion later in lecture 3, but now you only have to know that the solution is something like this. So Hij or H lambda, whatever, is proportional to 1/8 times exponential, I think this is plus already. So this is the solution you have. And by having this, we can prove the equivalence of this expression and this expression. The only thing you want to know is what is the coefficient here. So if you assume that this is equivalent, this expansion, let's say expansion 2, is equivalent to expansion 1 in the limit of a goes to a naught, which means now you can prove this equivalence and fix this coefficient. This is problem 6. Okay. I think the because of the bad internet, I have wasted too much time, and the content for the first lecture is very difficult to be finished. I will skip the part of the interferometer. That's something I think we may talk about. But the only thing you know is that for the stochastic gravitational wave, we are observing something like the spectral density, which I will define later and compare with the noise. Now I just go to the energy density of gravitational wave. I hope I can finish that in 10 minutes. Okay. If you remember, in the beginning of this talk, I very easily kind of mimic the energy density by comparing the Friedmann equation and the metric, which is influenced by a set of gravitational waves passing by. I have rho GW, if you remember correctly, is p squared of h squared of some something like this. Now this is what I have, or in this manner that you can understand better. H dot squared. So in this section, I will prove it in a more kind of a accurate way, but not so easy, but you can understand why it is. So firstly, we have the expansion, g mu nu x is g mu nu bar x plus h mu nu x. where you have h mu nu is much smaller than 1. This is the necessary condition. And the key point for this G mu nu bar is that it is not Minkowski, but some arbitrary but stationary metric. Like for instance, the FLRW metric, for instance. The key point of such analyze for the energy density is to split the metric into 2 different parts, for the high frequency part and low frequency part. For instance, if you are using the FLGW, so the Friedman, the Mercer, Robertson, Walker, if you have this, then this G mu nu is something like, let's see, this minus 1, a square, a square, a square. So the time evolution of this, let's say for instance, G mu nu dot is like a dot over a times G mu nu, something like this, right? So this is Hubble G mu nu. As I said, everything on the background evolves as Hubble. So the characteristic time scale, or equivalently, the time characteristic length scale of this G mu nu bar, sorry. Okay. So this G mu nu bar is h. So characteristic time scale, time or scale is h minus 1. Or characteristic frequency is just h. So this is the background. And its feature is that it is long and the low frequency is very low. That's what we can learn from it. And there's another part which we put it in this h mu nu. Depends on very high frequency and very short characteristic scales for change. So for instance, it has a characteristic with length of lambda. So lambda is much smaller than h minus 1, or frequency, which is much smaller than h. So this is somebody called LB. This is the length scale of the background. So we have such kind of division of high frequency part and low frequency part. We can always do the separation expansion of this, right? Next task is to expand the Einstein equation. So we know that the metric can be expanded, and also the Einstein equation can also be expanded. So we know that this is the Einstein equation. With R mu nu expanded as mu nu bar plus R mu nu 1 plus R mu nu 2. For R mu nu 1, I mean it's order h, and R mu nu 2 is order h squared. You have all of these orders. But this one is only a function of G mu nu bar. So this is a static and low frequency and long characteristic and length part. And then you can expand in this way for all of this Einstein equation. The key point is that the low frequency part has the background, for instance. And let me just write it here. So R mu nu bar, this is the low frequency part. Equals to, roughly speaking, you must say that the source term is has a low frequency part, right? And for high frequency part, it must be 0 on the left-hand side. So you can move this part to the right. Then you have this one again for the high frequency part. And also, you also have RMU2 for the high frequency part. Just to move this part to the right. The key point is that the second order part of the rich tensor also affects the low frequency part. This is because if you look at here, you have two of these wave numbers, right? And the characteristic of wave number of R mu nu is a sum of, let's say, so you have HK1, you have HK2, something like this, right? And the characteristic wave number is K1 plus K2. If by any chance K1 is approximately minus K2, then you have the then you know that this R mu nu to the second order has a sum of K approximately to 0. So this is a low frequency part. Later see it is indeed the case because everything we calculate the gravity energy of the gravitational wave, we are putting it into some average. I'll talk about that later. And you have a delta function, something like this. So this means that it's two of these frequency modes with the same frequency but the opposite direction. So in that case, it cancels each other, and the total Ricci scalar is of the low frequency part. So I think this is the most important thing for the argument in this equation. And by this, I can define the equation of motion, the energy density contributed by the second order Ricci tensor from the metric perturbation of the linear order. The key point is like this. So I will not write down explicitly the Ricci scalar in the linear theory, but the key point is that we, from this, the most important thing is to get the low frequency part from the second order Ricci tensor, right? Can I have five extra minutes? I think that's what I needed to finish this part.
Yeah, I think that would be fair given the technical difficulties we had.
Okay, thanks. Okay, so the trick is to do an average of the large enough volume or long enough time period. So we know that the low frequency and high frequency part are departed by, for instance, the condition of lambda is much smaller than the background length, which is Hubble, by the way, in the cosmology. And the frequency is much larger than the background frequency, which is also Hubble in this case. So we have insert a characteristic average scale L, let's say, to make lambda much smaller than L, much smaller than LB, which is Hubble length. F is much larger than L and much larger than FB, which is just Hubble. And make average of this, average over the volume of the L cube, for instance. So you have something like this, and make this as average. denoted by this angular bracket. In this manner, you can pick out the high frequency part from like, for instance, this part or this part, whatever. So then this equation, this color box equation, can be rewritten in this way. So R mu bar is minus R mu 2 plus number times T mu minus T mu T in this way. So this is what we have. This averaging is something like smeared out the unrelated high energy physics, and similar to the renormalization group in the particle physics theory. And by this way, we can have the contribution to the background from the gravitational wave. That's what I would like to do. For instance, if we define the energy density, energy momentum tensor in this way, then you can have that the Einstein equation in the so-called low frequency level has this form. So this is what we have. I think we'll use the T0I as this the energy flux next week. But in here, we only use the T, not, this is the just energy density. So let me write it down explicitly that I do not have much time, so I will not write the, okay. In this case, the key point is that you need this part, the second order Ricci tensor, right? Let me just write it. I mean, 2 half a bit mu theta mu. Okay. So we have this second order of the Ricci tensor. And then we further simplified by these conditions. First one is that we are talking about something without a source. So we have the equation of motion of this. We have a Lorentz gauge. And we also have a traceless condition. Note that we do not have TD gauge here because there are 3 degrees of makes H equals to 0. But so there are 2 physical degree of freedom and 3 gauge artifacts. And then it is very easy to see that all of these terms, let's see, so because of this, so this is 0, because h is 0. And you have all of these Lorentz conditions. So this is 0. And you can use the integration by parts. That's the reason why you can, for instance, this beta can go in this way. And then in something like that. So this is 0 because this alpha goes in this way. And you have this. This is a trace, so it's 0. This is the on this, and Lorentz condition is 0, Lorentz condition is 0, Lorentz condition is 0. And the only thing you have is this one and this one. But they are identical if you just put the indices the other way around. So you have our menu is 1/4 of h alpha beta mu h alpha beta mu. And but the average of this is 0. This is very easy to be seen from here because it is g mu nu, sorry, bar h alpha beta mu h alpha beta mu. And you can put this side, right? And then you put it this here. So it's h mu nu, h, something like this, right? And then you have the same condition of box h mu nu. So this is, right? So in this case, you substitute this one and this one back into here, you have the final result. The T mu nu is this. This is energy momentum tensor in the point of view of the so-called short wave approximation, and we can immediately find its energy moment, its energy density, which is this Hij dot. Sorry, this is squared. Those. All right. And this is, if you expand it, this Hij is H cross Eij cross H cross Eij cross something like this. You have H cross squared plus H cross squared. I still have some contents on the energy flux and the how to interpret this in cosmology, but I think I would better just stop here and leave the remaining context to the lecture tomorrow.
Okay. Hi, there's a question in the chat window. So Preetam asks.
Sorry, can you wait for a moment? I will try to reconnect with my computer. Then I can see the questions better.
Okay, I can actually
Please
just
wait.
read the question out for the moment.
Okay, yeah.
So the question is, the two polarizations H plus and H cross, are they independent of gauge transformations that you talked about? That is, are there any other kind of gauge transformations that give different polarizations of gravitational waves?
Okay, so now I can see the chat. I think this is independent of gauge transformation. Yeah, but in most of the models, H plus and H cross are basically the same, especially for the primordial gravitational wave. But there are some models, for instance, the inflation, the gravitational wave induced by some gauge field, that you can have different H plus and H cross. And this will give you a huge amount of the chiral gravitational wave in some sense. But gauge transformation is just choosing of a coordinate. This will not change anything for the polarizations. Did I answer that question? Yeah, I'm still using my iPad for speaking, but I can switch to my computer to make it easier to access to any questions. Okay, so
Okay. So does anybody else have questions at this point? Please just feel free to speak up.
why do we always consider flat image instead of non-flat? Okay, this is something that I think I will not cover in this lecture because this is purely an observational fact that due to the observation from, I think from WMAP and Planck, that the curvature term in the Friedmann equation is rather small. So in this case, it is convenient and theoretically reasonable to set the special part of the FLRW metric to be flat. For theoretical reason, this is because of inflation. So inflation will kind of wash out any of the inhomogeneities in the observable scale. But of course, if you go beyond the observable scale, like for a scale that is much, much larger than our observable universe, it is indeed possible that the universe is non-flat and even topologically simple. I mean, that's something which is rooted in the essence of the quantum gravity. But fortunately, we do not have to care about that for our observations, because in the current observation patch, which is inflated during inflationary era, to be very flat. Okay. Are there any questions? I can open my video. Yeah, I have left some problems. I think most of them are just algebraic calculations. I think they are not so difficult to be solved. I already asked Swagat to take a look at it, and he said it is okay. I believe it is okay for all of you. And but in the later lectures, I may make up some difficult problems to make you happy. If you have any questions, then you can ask the tutors in the tutorial session.
Great. Thank you, Shi, for today's lecture. And let's all reconvene in about an hour for the tutorial.